Hey everybody, it's MC here from the Little Hill. This is our third episode of our TIS-100 playthrough, and before we get started, I just want to say that it took 2 episodes to get through the last 2 challenges, and I'm hoping to speed this up a little bit. So I went ahead and I solved the next 3 challenges, and we'll see if we can't get through those in this one playthrough. So, without further ado, let's go into challenge number 3, the differential converter. Alright, let's check out this debug. Interesting. It looks like there's some kind of static memory in this thing. Encoded something or other. Okay, so there's something encoded inside the computer, so we'll have to figure out what that is. Alright, interesting. Anyway, this differential converter is asking us to read values from in A and in B and write in minus A, or in A minus in B to out P, and in B minus in A to out N. Now, knowing that in A is the same for both of these operations and in B is the same for both of these operations, one thing that we can immediately see is that one number is just going to be the inverse of the other number. So in other words, we just have to calculate this answer once, and then using this command right here, the negate command, we can get the answer for the other output. So, first of all, we need to take in B, and we're going to move it to the left so that we can process it in A. Now, in A is going to move up to the accumulator, and then we're going to subtract right. So, that is taking in.A and subtracting in.B. Next, we're going to move it down, and then we're going to move it down again, and then finally, in this node, we're going to move up to the accumulator. And the reason we're doing that is because we need to write that value downward, but we also need to negate it, write it to the right, and then write it out. And so because we are passing it into two different locations, we need to save it somehow, because if we were to just pass it down, then we would lose the value and we would have nothing to pass to the right. So we save it to the accumulator. Now, since what we calculated up here was in.A minus in.B, this is immediately what's going to be passed to out.P. So without having modified the value, move accumulator down. Now, we need to modify that value for out.N. And like we said earlier, it's just going to be the negation of in.B, or excuse me, the negation of what we're passing to out.P. So we'll just write neg, which negates the accumulator register, and we're going to move that value to the right. And then in this last node, we'll move left, down, and that should do it for us. So, knowing this program will be the shortest possible one for instructions, cycles, and nodes, I'm just going to name it NIC for nodes, instructions, and cycles, as we have been doing for the past ones, and let's just run it to show you. All that output looks good so far, and the random output looks good. So something you guys may not know is that the first output that it shows you over here, or the first inputs I should say that it shows you over here, for the first run will stay the same for every run. Every time you run the program. And that is what your program is based on over here. However, the second run is based on randomized input. And so that is to see, because if you hard-coded it, you wouldn't get the next run right. And so that random input is just there to double-check you. So we didn't quite get the lowest number of cycles. We did get the lowest number of nodes possible, and we did get the lowest number of instructions. So for some of these, I may come back and I may try to optimize them as far as I can. Most I think I will leave as is. I mean, I'm trying to get these as low as possible without putting too much work into it. But if we look at it, we could probably make it faster by making this parallel. In fact, let's see if we can't do it right now. So this is going to, well, here, I'll show you what we can do. So this didn't have the cycles, but it did have the node and instruction, I believe. Yes, least amount of instructions. Let's see if we copy it. What if we did this? What if we moved the accumulator to the right? And I'm solving this in real time, so, you know, I may mess this up. You guys will have to check me. And we want to move this guy to the accumulator. We want to move, or we want to oh, goodness, how are we going to do this one? This is interesting. You know what we could do? I don't know if this will be right, but let's try this out. Move up, right? No, excuse me. I'm going to Control Z just to undo all this. Okay, Control Z. So, if we compute these right here, I'm thinking if we can pass this over, then we don't need to negate it right here, and then maybe we can do it faster? I don't know, we'll see. Move accumulator down, move accumulator right. And what if we did a move left, down, move up, down. We're going to get rid of these last two. And we are going to change this to be move up, accumulator, negate, move accumulator down. I don't know that this will be any faster. Let's check it out. In fact, it's not. It's slower than our original solution. So, you know what? That's fine. It happens sometimes. I don't solve these things on the first try usually. But maybe we can come back to this one later at some point and we'll see. We're just going to erase it since it didn't perform better in any area than our last one. So some of you guys who are watching this may be screaming at your screen right now. Sorry, it wasn't so obvious for me. But let's move on to the next one. This is going to be challenge 4, signal comparator. All right, let's open this flavor text. Found a block of static memory, but it's in a proprietary format I never saw before. Can't make heads or tails of it. Oh, brother. There's just too many different kinds of machines coming out now, and I like tinkering with them as much as the next guy. But when every Tom, Dick, and Mary implements their own memory address scheme, it's all and then it's garbled. I say the bottom's going to drop out of the microcomputer market. Soon. Mark my words. Alright, so this is the signal comparator challenge. Read a value from in, write 1 to out.g if it's greater than 0, write 1 to out.e if it's equal to 0, and write 1 to out.l if it's less than 0. When a 1 is not written to an output, write a 0 instead. So here is how we will accomplish this one. First of all, we need to move the input from up to down. Control down will move where our cursor is. We're going to move up, down, control down again, move, and this time up, right, to move it to the right. Now, we need to have a block here that is going to move the value from the left to the accumulator, because once again, we're going to do some processing in this block, but we also want to pass it to the right. So we're going to move that accumulator value to the right, where the right will process it for out.e and so on and so forth. And then finally, what we're going to do is this first one, out.g, outputs a 1 if the value is greater than 0. Now if we look at our command set, we have jump greater than 0, and it'll jump to a label. So check this out. If we do jump greater than 0, and we have a label called greater, then we can write greater here, and it'll jump to that label, and the command we're going to put under that will be move 1 down. Now, if it's not greater, it's just going to go to the next command. Well, the next command is going to be if it's 0 or less than 0, in which case we want to output a 0. So we'll go move 0 down. However, we don't want it going to this command next because we don't want to output a 1. So what we need to do is we need to jump back to the start. And there's two ways of doing that. I'll show you one possible way with this first block, which is jump start. And so we'll just add a start label right there. And that is that first block done. Okay, now let's move on to this one. Start. Actually, we're not going to use start in this one. I'll show you another method with this block. We're going to move that value that we're receiving from the left, and we're going to move it to the accumulator because, once again, we want to perform some operations on it and pass it to the right. So we're going to move accumulator right. And then this one, we're going to output a 1 if it's equal to 0. So we're going to do a jump if equal to 0, and we're going to jump to the label 0. So label 0 is right here, and we're going to say move 1 down, just like that first one. And since it's a different command, it'll operate just how we want it to. Now, once again, if it's not a 0, then it's just going to move to the next command, which we want to be moving a 0 to the output, so we're going to move 0 down. And then finally, we want to go back to the start because we don't want to move this 1 down again after we've moved that 0 down. So the second way that you could possibly do it is you could do a JRO, which means jump relative offset. So that's going to take a number like 1 or 2 or 3 or whatever and jump that many registers. So if we put jump 2, it would jump 1 command, 2 commands. Now there are no 2 commands. If you put like jump 1, it jumps to the next command, which would be this move 1 down. Or alternatively, check this out, you could put in negative numbers. If I put -1, it jumps to the command before and then performs this and jumps to the command before and so on and so forth. So it would get caught in an infinite loop. So instead we want to do jump -1, 2, 3, 4, -4 lines, and that should be our jump. All right, and then finally, let's write this last block. Start, move left to the accumulator where we can compare it. If it's less than 0, JLZ, we want to move to less. And then we've got that less block, move 1 down, and finally move 0 down if it's not less than, and we're going to jump to the start. And that should be our program. Let's check it out. That went really fast, but there you go. You can see we got the fewest number of instructions, fewest number of cycles, fewest number of nodes. So let's name it in our usual style. Nodes, instructions, cycles. There we go. Now those of you who really know this game, there are people out there, I've looked, and they have solutions to some of these problems, or claim to have solutions to some of these challenges that get less than what you see on these histograms right here, which could totally be plausible. I mean, if few enough people are getting them, they're not going to show up, and so I may not be reaching that, but well, I don't know. I'm trying my best. I'm getting to the bottom of what I can see on the histogram for the most part, and so yeah. Anyway. So if you've got some interesting solutions, let me know and I'll try them out. Maybe I can put them up here if you want me to. But otherwise, yeah, I'll just keep going along. All right, and so the last one we have for today is the signal multiplexer. Let's check it out. All right, so some flavor text right here. I might have an idea of where this TIS-100 machine came from. Zero described the architecture to Fred at Motorola, and he says it sounds like it was designed for signal processing. That got my brain going. Zero, government project maybe, something the CIA cooked up to comb through Soviet radio signals. Hush hush. Top secret. FP. Maybe. Could I be in possession of a classified device? Something for spooks? I might have to sit on this one for a while. Alright, so this is the signal multiplexer. Read values from in.A and in.B. Read a value from in.S. Write in.A when in.S is -1. Write in.B when in.S is 1. And write in.A plus in.B when in.S is 0. Alright, so the first implementation we're going to go for is probably, in my mind, the easiest one. Now, because we need in.A, we're going to do all of our computation in this middle block right here. So we're going to move up, right, to get this value from here into the center block. And we're going to move up, left, to get B to the center block as well. Now for this one, remember that start label that we had? We're going to abbreviate it to S so we can have it on the same line as our first command, which is going to be move up accumulator. Now we're going to be doing some logical operations on this S, so we need to move it to the accumulator, because you need to do, in order to do comparisons like jump if greater than or jump if less than, you need to have it in the accumulator. Speaking of which, our first command is going to be jump if greater than 0, and we're going to jump to G. So the reason we're having this jump is because we want to execute a specific set of code that is going to output the proper values, and we will have that G label. We'll just put it right here. It's going to move around in a bit, but if our S is greater than 0, if we check back over here, that means it's a 1, because the S is only ever going to be a 1, -1, or 0. So if it's greater than 0, it's a 1. We want to write out B. So we're going to move right, down. Then we're going to move left, and check it out. Because this is trying to come in, we need to do something with that input. But we don't want to move it down, because we don't want to move it to the output. And all we're going to have in these blocks is move up, down. I mean, like I said, we're having all the logic up here, so every other block is just for transporting values. And as you can see right off the bat, this is the minimum node implementation, because we've got input here, input here, input here, and output here. So this is the easiest way to connect all 4 ports. Okay. Now, like I was saying, this value needs to go somewhere, otherwise it's just going to block this. So we have to move it, but we don't want to move it down. We don't want to move it to the accumulator necessarily. I mean, we could move it to the accumulator, but, you know, that might just make things messy. There's no reason for it. Instead, what we can do is, I don't know if it's in here, it's not listed, okay. What we can do is we can move left, nil, and that just throws the value in the trash. Pretty neat. All right, so with that completed, we're going to jump back to the start. Now the next thing we want to do, if it's not greater than 0, then it might be less than 0. And if it's less than 0, we want to jump to L. Okay, so L is going to be right here. We're going to move. Now, like we saw, if it's less than 0, it's going to be a -1, which means we want to move in.A, the left value, down to the output. So move left, down. And then just like we did right here, we need to trash this value right here, because we're not writing it anywhere and we're not performing any operations with it. So we're just going to move right, nil. Now, because this is the last logical block, this is just going to curl around and come back up top. So we don't need to put a jump start right here, because after it completes this last instruction, it's just going to cycle back around. All right, so we've taken care of the greater than 0 case and the less than 0 case. Let's take care of that one last case. Now, if it's not greater than 0, it'll move to the next command. If it's not less than 0, it's going to move to the next command. Here is where we're going to put that next command. That next command is adding in.A to in.B and moving to the output. So first of all, we're going to move left to the accumulator. We're going to add the right. We're going to move the accumulator down. And then finally, we're going to jump back to the start. And that should be it. Let's check it out. Oh, and because I know ahead of time, we're going to name this implementation, I believe, is the node and instruction count implementation that minimizes those two values. So it's looking good so far. It's going through the random output just fine. Beautiful. All right, so cycle counts, it wasn't the best, but node counts and instruction counts, it was the best. All right, return to the segment list. Now we've got one more. We're going to go for those cycles. Now, if you remember in an earlier challenge, one of the things that we had to do was we used parallel computing to make this go a lot faster. Now here's how we can do that. Say, for instance, we add both these values together every single time. But, and that in itself would speed things up because then we're doing less comparisons. But if the value is -1 or +1 or whatever, and we don't want to operate with in.a, we just change that value to a 0, or we just pass a 0 instead of passing the value. And then we add the 0 to the b, or we add the 0 to the a, and then pass that out. Or alternatively, we just pass a or b and add those together, and that should distribute the calculations that we need to make and speed this up. So I'll show you how we're going to do that. We're going to move up to the accumulator. Then we're going to move accumulator to any, move accumulator any. So this first one's going to move it into the accumulator from S, and then it'll take it to any that's ready right away, one of these two, and then the second one will do it for whichever one didn't just receive. Okay, so we're going to put a start label right there, like we have in the past. We're going to move that right value to the accumulator. Now, if the value is a -1 or a 0, we want to keep a. So we want to get rid of a if it's greater than 0. Jump greater than 0, we're going to jump to greater. Now greater means that we don't want a, right? So what we're going to do is we're going to move 0 down, and we're going to move up nil, because we need to trash that value. We need to get rid of it somehow. But if it's not greater than 0, it's -1 or 0, which means we do want to keep the a. So we're going to move up, down, and we'll just jump back to the start. Pretty neat. So we just take that value from right here. We're going to move up, right, and then we'll do something similar over here. So we're going to write start, move, left to the accumulator. There we go. Now check it out. We want B in the case where S is 1 or 0. If it's not 1 or 0, it's -1, which means that it is less than 0. So jump if less than 0. We're going to jump to less. So less is going to say move a 0 down, move up nil, because once again we need to trash that value so it doesn't block our input port. And we need to move a 0 down because we don't want to keep that B. The 0 is just the additive identity, so adding 0 to anything just gives you whatever you previously had, right? So that's some pretty basic math for you. All right, so, but similarly, if it's not less than 0, that means it's a 1 or a 0, which means we do want to keep the value. So we're going to move up, down, and we're going to jump back to the start. We're going to move this value from up to the left, and then here we are going to move any to the accumulator. and we're going to add any. Alright, so it's just going to take whichever one comes to it first and add it to the accumulator, and then it'll take whichever one comes second and add it to the accumulator. And we're going to move the accumulator down, and then we're going to move up, down. Alright, that should be it. This should be our instructions, no, excuse me, our cycles implementation. Let's check it out. See, you can already see it's going faster. Look at how fast that's going. It's looping right there. It's going as faster, much faster than the other one. And you can see, indeed, 203 cycles compared to, I don't know, I think the last one was like 280 cycles. Now, it was more nodes and it was more instructions. But like I've said before, sometimes you have to have a little bit more complicated architecture to get a little bit faster performance. Anyway, thank you guys for watching. This has been episode 3. We'll come back with episode 4 where we can maybe knock out another 2 or 3 challenges. But until next time, see you guys later. Bye.